Welcome to the Cosmic Pie Podcast, Season 2, Episode 14. I'm your host, Wayne Barkhouse, and with me is
Robert Moore.
So we are broadcasting live from the campus of the University of North Dakota here in very beautiful Grand Forks.
It is today.
Really beautiful day.
It's really
out there.
beautiful day today.
It really brightens up the campus too when you walk around on a nice
Yeah.
clear sky day with the sun shining, and it's fairly warm too.
It's fairly warm. It's really warm for this time of year here.
Yeah, really nice out there today. Now, we do have a live chat feature, so if you have any comments or questions throughout the podcast, please do not hesitate to use that feature. And also, if you like this podcast, please give us a thumbs up. That way we know people like it. But don't give us a thumbs down, even if you didn't like it. Just don't do anything. How's that?
I like that idea. Yeah.
Positive or remarks
gets,
or no comments at all, right?
It gets back to that old saying of, if you can't say nothing nice, don't say anything at all.
Don't say anything at all.
Yeah.
Okay. Now, today we're going to update a couple items to start with. Okay. So the first thing we're going to start with, if you go to the first slide, Robert.
All right.
The first thing we're going to look at then is an update on the Voyager 1 spacecraft. So we had really a positive news that had come out recently. In fact, Saturday, that they are finally back in communication on a regular basis with the Voyager 1 spacecraft. So what happened roughly 5 months ago is that there was a corrupted memory on board the computer, the hardware of the spacecraft, and that caused the spacecraft not to be able to send useful signals back to the Earth. Now, to give you an idea of what this is, if you don't remember or never seen it before, back in the 1977, NASA launched a pair of spacecraft, I think within a month of each other, if I'm not mistaken.
Roughly, yeah.
And the primary mission of these two spacecraft was to observe the outer planets and the gas giants, Jupiter, Saturn, Uranus, and Neptune. And it took advantage of what we call the grand alignment, where they discovered that if you could go at a certain time and reach Jupiter, you could use Jupiter's gravity to give you an extra boost to send you on your way to Saturn. And when you get to Saturn,
you could use it to boost you onto Uranus and Neptune.
Right. So it was kind of a cheap way to explore the outer solar system in terms of you didn't have a massive mega rocket that you need to launch. And of course, what that really means is you didn't need to spend all that extra money to maybe, in the 70s, they could have, paid for probably a Saturn V-like rocket and boost each spacecraft into outer solar system using that.
I think weren't they launched on the last couple of Saturn V's?
No, they actually launched on the Atlas Centaur.
Oh, okay.
So the last Saturn V that was launched was to put up the Skylab.
Skylab, right.
And that was, I think, in 74, roughly.
Right. Which itself was the fuselage of a first stage of this.
Well, it should be the third stage.
Was it the third?
Or second stage. I can't remember. I think it was the second stage.
Okay.
Right. I knew they used the Saturn 1B, which is a smaller family member to the Saturn V, to launch astronauts. But Skylab itself was put up on a Saturn V.
Yeah.
And I believe they use the third stage as hollowed out tube type of thing in the lab in that.
Okay.
So they would need the first stage and the second stage to get it into a nominal Earth orbit. So the third stage it was empty, right? They hollowed that out and put the laboratory inside of it, because normally that would, the outer part of it would house the lunar module.
Right.
And then it'll give you that extra boost to get you onto the moon during the Apollo days, right? Yep. So they could use that. They didn't need that third stage to put something just into low Earth orbit. Yeah. So that's where they built the Skylab out of that. So the idea was, the Voyager spacecraft, the two on Voyager 1 and 2 was launched before 1.
Yep.
Which is kind of weird because I guess the press didn't like that at the time. But the second one that was launched was on a slightly faster trajectory, so it actually got to the first target, Jupiter, first. So that's why they call that spacecraft Voyager 1.
Yep.
So they were both launched on an Atlas Centaur, and I think that when you propose a mission, which is something we talked about a little bit last week on our podcast with Bonnie Beretti, when you propose a mission, it takes a lot of time, leeway, right, from the time you initially propose it to it gets launched. And you could talk about, it could be 30 years in some cases. Right. And when this type of program was first announced, the idea, I think, was to set up multiple spacecraft. In fact, I remember reading some of the initial plans were something like 4, at least, spacecraft. Right. And so there's built-in degeneracy or redundancy in the fact that if a couple of the spacecraft failed along the way, because it's a long time, right?
It's a long time.
You get to Jupiter in about 1979, at least the first spacecraft, but then Voyager 2 takes until 1989 to make it to Neptune. That's a long time to fly through interstellar space. Anything can go wrong.
Through inner solar space.
Well, yes. Outer solar system space.
Yeah.
That was a Freudian slip on my part,
Yeah.
because I wished we'd be able to send spacecraft into interstellar space.
Absolutely. Well, Voyager 1 is getting there. And that's one of the reasons they want to try to keep in touch with us. But I'll point out something. It's 47 years old, right?
Yeah.
This is the oldest continuously operating computer in existence.
Yeah, isn't that something?
That's something. I mean, this is 1970s actually probably 1960s technology.
It would be 1960s.
And it's still operating.
Yeah, and so the reason why it's such a delay is there's some engineering cutoff when they're developing the technology, because it has to go through lots and lots of tests and harden up for radiation and stuff, right? You get
Right.
a lot of exposure to cosmic rays and so on that you have to worry about, and that can cause damage to the hardware, so you want to harden it up. So there's some point in time where they say, okay, production stops here.
We go with what we got.
We go with what we got, and we do the best we can and do all the things that we need to do to protect it and get it ready for validate it for space launches.
Right.
And so then the technology gets frozen. So for Voyager 1 and 2, it was probably late 60s, early 70s technology
Right.
that it's
went
based
into
on.
it.
And it's still working
And it's
today.
still working.
It's amazing when you think about it.
Yeah. I mean, to me, that's one of the amazing things. Because, 47 years. And when it was built, it was 5 to 10 year old technology when it was put together.
Now in the 70s, if you were around at that time, I mean, the economy, I guess, wasn't doing too good, right? I mean, it was a hard period for the United States. Wasn't this back in the time where people would line up at the gas station during the oil crisis, right? There was oil embargo from
which was not really a crisis, but it was blown out of.
But it was an oil embargo type of
Yeah.
situation, right?
Yeah.
I don't remember any of that stuff. but-
OPEC basically rose, if I'm remembering it correct, which I was a little kid. OPEC
Yeah.
got together, the oil producing countries, and they raised their prices, which in turn led to America was not prepared for it, so it led to a lot of shortages.
Well, I think
Sounds familiar.
I think it's fair to say that the United States went through an economic downturn
Yes,
in the 70s.
that is fair.
And I know that some of the Voyager, so initially, let's say it was 4 spacecraft that was to be launched. I think President Nixon at the time, I believe he was the one responsible, that he basically cut it in half and said, okay, we'll provide enough money for NASA to fund 2 of these missions.
Right.
But that's it. In fact, they probably would want to do 1, but then you say, okay, well, we want to at least have to have 1 backup just in
We
case
want at
one
least
fails.
one backup.
In
Right.
case one fails, yeah. So the Voyager program has been one of the most successful programs in the history of NASA for exploration of the solar system. So Voyager 1 today, even though it was launched way back in 1977, it is so far away that it takes light about 22 and a half hours one way to reach the Voyager spacecraft. It's amazing. Now, if you're not familiar with the speed of light, if you could travel the speed of light around the Earth, for example, if you could do that, you go around the Earth about 7.5 times in only 1 second.
Right. Or you can look at it, the sun is 8 light minutes. It takes light 8 minutes to get from the sun to Earth.
And the moon's about 1 light second away. It would only take you about a second to get to the moon, traveling at the speed of light.
Right.
And yet the Voyager spacecraft, at least Voyager 1, is so far away, it takes you almost a whole day for the signal to get there.
That's impressive.
So if you sent a command like, I don't know, tell me you're still alive, text me hello world, it would take 22 and a half hours for that signal to travel from the Earth to the spacecraft, and you'd have to wait another 22 and a half hours for the signal to get back on Earth. So you'd have to wait, 45 hours to get the result of whatever you command the spacecraft to do.
Yeah. But the reason we shut down, if I'm remembering correctly, Voyager 2 was shut down because it had reached the limit of what it could do, wasn't it?
No, so what happened was when Voyager 1 flew by Jupiter, and before it flew by Saturn, they had an option. We can go very close to the largest moon of Saturn, Titan, and try to get some detailed images. Or we could go not so close and that'll allow us to fly onto Uranus and then eventually Neptune.
Okay.
So what they decided to do is, because Titan at the time, so this would be, let's say, in the late 70s, the idea was that Titan has an atmosphere, as we know.
Yeah.
And therefore, maybe conditions were right for life to arise on its surface. So it might be worthwhile to at least sacrifice one of the Voyager spacecraft, have it fly as close to Titan as possible, but knowing that it would never go on to explore any other planets.
Okay, so that's what happened.
So that's what happened. Now, in hindsight, which is always 2020,
right.
When Voyager 1 flew by Titan, it turned out Titan in the optical is so opaque. There's so many, the clouds are so thick, they couldn't see the surface, and that's ultimately what they had hoped to see, is the surface. Maybe to look for lakes of methane,
right?
Hydrocarbon lakes, which we think, and since that time, of course, we've landed a space probe on the surface of Titan.
Pretty much found them, yeah.
Yeah, and so at that time, though, when we flew by Titan for the first time, the very good view. Now, this is not the first time we flew by Titan. Pioneer did that a couple years before that, but in terms of the quality of the data, it was really poor, the resolution of the images and stuff, and Voyager was far superior. So when Voyager 1 flew by Titan close up, and they were a little bit disappointed because they weren't able to see the surface. But it was too late at that point, right? The spacecraft then was on its way out of the solar system, never to ever go by another planet again that's in our solar system.
Yep.
Now, so what happened when Voyager 2 arrived a little bit later at Saturn, it was put in a trajectory, a path, that would see it not get so close to Titan, because there was no point, but have it fly on to Uranus and Neptune, which it did. In 86, it flew by Uranus, January of 86, and then it flew by Neptune in August of 1989.
Right.
And then that was it. So there were no other encounters. It wasn't able to make it to Pluto. And we've done that since with the New Horizon spacecraft.
It is so energy intensive and time intensive to fly one of these missions to the outer solar systems. It's a feat in and of itself. So, yeah.
There was thought, and it hasn't been launched yet, but there was the European Space Agency was thinking about launching a couple, let's say a pair of spacecraft, in orbit around the sun with probably ion propulsion engines.
Okay.
Which produce very little thrust, but something you can run for thousands and thousands of hours and then build up a change in your velocity and your acceleration. Right. And have them just out there so that if a comet or some interesting object was discovered passing through the solar system, they would be able to redirect these spacecraft. Right, to intercept it.
That would be cool. That's a cool idea.
It is, because we've had, just to get down a little bit of a sidetrack, we've had indications of 2 objects at least recently that have flown by, passed around the sun and outbound again, never to return on these hyperbolic trajectories, which are not bound orbits around the sun, that came from interstellar space.
I'm sitting here going, talk about putting an orbit around one of those things and hitch a ride.
Yeah. Imagine you had to land or just land on the thing and transmit as much as you can until the signal gets so weak you couldn't be able to. Well, that's it, right? So it's kind of interesting, but I know the European Space Agency is looking at that. In fact, they may be doing that. It just hasn't been launched yet. But that would be an interesting sort of thing to do. Absolutely. The point here is it's very difficult to dramatically change the orbit that your spacecraft is in without having a way of doing it. And the old chemical rocket days, it would require a large rocket.
With a lot of fuel.
A lot of weight, a lot of money, in other words.
Right.
But with these ion propulsion engines, which are relatively new, at least since the time Voyager was launched, they've been used. That's the way to do it, very gradually and slowly. But of course, the Voyager missions didn't have that technology.
Right.
That wasn't ready to fly in the late 70s.
To me, the big thing, and why we're trying to keep Voyager 1 online, is it's at that point where it's crossing out of the sun's magnetosphere, the sun's magnetic influence, and crossing into interstellar space, where interstellar magnetic fields and particles dominate instead.
Yeah.
So that's something to try to keep it alive for.
That's the slip I made. In fact, that now its mission is to explore in the interstellar medium. That's the mission it's on, the long-duration mission. And so it is becoming our first interstellar explorer, if you like, our first emissary from Earth that's going out into orbit around the center of the Milky Way, essentially.
Essentially. Yeah.
So it's kind of cool when you think about it. So if something dramatically and bad happened to the Earth, we'd still have these, items out there, these artifacts.
3 of them.
That would represent a long lost culture. In fact, there's actually more than that. So if you
I
think,
knew
what are
something.
all the spacecraft that have reached escape velocity from the sun? Pioneer 10 and 11.
Okay, I forgot about the Pioneers.
Yeah. Voyager 1 and 2, and the New Horizon
New
mission.
Horizons.
So there's actually 5 spacecraft that are moving away from our sun all of the time and will be in orbit around the center of the Milky Way.
Right.
Which is, like I said, it's like a time capsule. The fact that it'll show that we existed no matter what happens in the future to the Earth.
Which brings up the question, do you shut it down and stop it from transmitting when it gets out there? Because then it could be a beacon.
Well, the problem there is that you need energy to transmit, and the energy provided to the spacecraft is the radioactive decay of plutonium.
Right.
And you put so much plutonium on board each spacecraft when it leaves the Earth, and there's weight restrictions, so it's not like you have an endless supply. But that plutonium, as it decays, it releases heat, and that heat actually gets turned into energy using a thermocouple.
Mm-hmm.
And that energy is getting weaker and weaker with time because you have less of that plutonium, radioactive plutonium that's available. So eventually, come in another few years from now, even the radio transmitter will be turned off or it'll die on its own. There won't be enough energy to power it.
Right.
But the spacecraft itself will forever be out there.
Yeah.
So if any other life form somewhere in the universe stumbles 50 million years from now across one of these objects and explores it, they'll know that we existed.
Yep.
They'll know they're not alone if they think they are at that moment in time.
There you go.
Imagine if we found some relic spaceship, that just happens to pass near our sun, like say 10 years from now, and we went out and looked at it and we could tell it was some robot that's long since died that was launched from some civilization eons and eons in the past. Wouldn't that be something?
That would be nice. I would love that, but that's me. I'm a little crazy.
Well, there's your direct proof of life, isn't it?
Absolutely. And of intelligent life. Intelligence at that.
Yeah. So the thing what happened with Voyager 1 is that it had a problem, probably a cosmic ray impacted one of the memory chips, and that caused issues with the computer. So it was starting to send back gibberish, essentially, nothing that was meaningful. And the scientists managed to isolate what part of the memory had issues, and they blocked that part off. And now they're able to engineer the software. And they couldn't hold the whole software packages that they needed to hold. So they actually split it up into modules and placed it in different parts of the memory. That's an ingenious
way of handling it.
It's incredible the amount of engineering that we can still do on this spacecraft for that old technology.
Especially since there's so very few people around who worked on it to know what to do with it.
Now, most of those people are retired, and a lot of them have passed away, unfortunately, by now.
Unfortunately, yeah.
But the thing is, it's very slow progress. It took 5 months to get it to where it is today because of the delay time is so huge, right?
Right.
So now it's got to the point where it's sending back commands on a regular basis, and they're working on reestablishing actual science output that's getting from some of the experiments on board so it can send back useful science data. And that should happen, in the next several months.
Here's hoping that goes well. Yeah.
So it's very interesting.
Yep.
Now, the other update we have for you, then, if you can turn to the next slide, is regarding this Dragonfly mission. We spoke about Titan already, so this fits in well.
Yep.
So Dragonfly is this essentially robot helicopter that's going to land on the surface of Titan and then fly around in its thick atmosphere to explore different regions of the Titan, which is the largest moon of Saturn. So we're gone. Just think of the difference now. We're going from just flying by Titan, imaging in a way using optical cameras that does not allow us to see any of the surface of Titan, to now actually landing helicopters, if you like, drones on the surface of Titan and be able to fly around and sample in situ directly different landing zones on Titan itself. It's just amazing.
I'm sitting here going, I understand how they can do it, and I'm still going, man, this sounds like science fiction.
There's a lot of work being done here at University of North Dakota on this type of work, right? And some people want, why do I need drones, for example? Well, here's an example of the use of this drone, which is just out of this world.
Right.
Right? It's on Titan. A moon, you don't need to send people there and risk their lives, right? Let's send the robots
Let's
first.
send the robots.
Do the exploration for us. It's a lot cheaper, a lot easier. You don't have to worry about killing anybody. All of these, and they can last for decades and decades and never complain about being hungry.
Yep.
As long as they got their energy, that's where there's their hunger, the source of food, I guess. As long as they got their energy supply, then they're fine.
Sea spirit and
Opportunity. Yeah.
We're slated to last for 3 months, and instead lasted for over a decade.
Yeah, and they were dragging their wheels behind them at the end and everything, right?
Right.
But it's just really interesting. And then just imagine what we'll get, 200-300 years from now.
Right.
What type of technology will we have, and how would that affect exploration of our own solar system and beyond, right? Interstellar space.
Well, I'm sitting here going, Titan could very easily be a fuel depot for us. I'm hoping we're using Saturn and Jupiter itself with the hydrogen there.
And don't forget the methane, too. It's available.
But the methane and ethane of Titan could easily be a fuel.
Well, we could, imagine flying by like Neptune and have ram jet type scoops that scoop up the methane from the outer atmosphere of Neptune and use that as a fuel supply.
To kick on further and faster.
Yeah. In fact, NASA's actually developing back to looking at nuclear propulsion again.
Right.
It's something that they had done, I guess, way back in the 50s and were very successful at it.
They had a working model.
Yeah, and then actually shut that program down for various reasons.
Various reasons.
It's nuclear, folks. There's a lot of safety issues you have to worry about.
Safety issues and safety of somebody else misinterpreting what you're doing with it.
And the other thing is,
launching.
When you actually launch a rocket, nuclear is not the way to go. The chemical rockets were the way to get you off the planet. Then once you're in the space, of course, then you could use nuclear propulsion to greater efficiency that way.
To which I've had somebody, actually say to me, oh, great, so now we're going to make space radioactive, which had me actually laughing before I could catch myself. So for those of you who don't know, space is radioactive. Okay?
Yeah. But the thing is, I mean, even I'm thinking of a scientist way back who had proposed the idea of throwing hydrogen bombs out the back end of the rocket.
Yeah, I don't remember who that was, suggested that.
It's a person, he just died, Dyson.
Was it Dyson?
Yeah, he was the one that suggested that. In fact, he actually worked, I think, on that project. It was either for a private group or maybe a government-related type of group to do just such a thing.
He was saying, let's detonate an H-bomb behind the spacecraft and use the pressure to thrust the rocket forward.
Yeah, the shock wave that would be generating an explosion. So you just keep dumping H-bombs out the rear end of this to propel you in the opposite direction. But that didn't go over too well. I mean, we're going to set up 1,000 hydrogen bombs in this rocket.
I'm in favor of, once we're outside of a strong gravity well like Earth, throwing out the sails and.
Especially for the inner solar system, right? But I mean, you need a huge, huge area sail if you want to get to the outer planets.
Right. Well, I'm thinking for interstellar because you could throw them out and use that little bit of push.
Like a shield. Yeah, to absorb.
Because you don't need a big strong push. You just like the ion engines, you just need a little bit.
Yeah, you just want to build up. I mean, you got to reach escape velocity from the sun.
Right.
And if you turn off your rocket engines, you do slow down because there's gravity of the sun pulling you back. It's not like you'd be traveling at a constant speed. You're still slowing down.
So that's where the sails come in. Is you keep giving you a little push.
Yeah.
So that you probably still slow down, but you're not slowing down as much.
Right. Yeah. So the update with the Dragonfly is that NASA has officially approved the mission, which is nice. So now people can actually start cutting metal. And finalizing the plans and start building the stuff.
Start building circuits.
And this is due to land on Titan in the early 2030s, like 2034 if I'm not mistaken. So this is going to be, that's not only 10 years from now. It's not a lot of time. So if you're younger, I guess it's not a lot of time. If you're older, it might be a lot. But it's all from your perspective.
I'm hoping to see it. Thank you very much.
As Einstein says, it's all relative, folks.
Right.
But yeah, you can imagine the fantastic science and data and the images that we'll get back from a mission like this. It's going to be incredible.
They're only going to keep getting better.
Yeah.
The technology is there and it's getting better. So.
Well, now I'm thinking about like Popular Mechanics, Popular Science magazines. They published articles, back in the early '80s saying this is what we should be by 1990.
Oh, Lord,
right?
yeah.
So there was these things, we were exploring the moons of Uranus and Neptune and on this place. And it's like none of it even came close to being reality because there was something realistic that showed up, and money, right? I mean, it's nice if you got endless supply of cash to support these missions. But, you're competing for a lot of other dollars that need to go elsewhere, obviously, right? It would be nice if we lived in a society where we could devote a large fraction of our resources, our money, to projects like exploring the solar system because we don't need it for anything else. We don't have a debt or a deficit of any type. There's nothing going on that we need to spend money on. That would be, great, but that's not reality, unfortunately.
Unfortunately.
Yeah.
Yep. So, it is what it is, but I'm glad, yes, this mission has been greenlit, and I'm glad for it. I'm looking forward to it. That's only about 10 years off.
Well, let's just say these projects will get done eventually.
Right. Okay.
They'll just take more time than what we wish.
Yeah.
Put it that way.
Yeah.
But then we don't have the type of vehicles that we're flying now, the drones and all that technology that didn't exist back in the 80s.
No.
So it would cost a lot less money to send up those type of devices. So if you're interested in working on drone technology, come here to the University of North Dakota. It's one of the main. Yeah, it's one of the main research areas. I'm thinking about it now because we're talking about this kind of stuff. But it's one of the main research locations here in the United States to develop this technology. So there's all kinds of things you can think of to do with these kind of devices. Right? It's amazing when you get down to it. Now, as another sort of interesting thing that I've heard about recently is the connection that was made between this crater that you see here in this image. Now, number one, this is an image taken with the NASA's Lunar Reconnaissance Observer, I think, LRO orbiter or whatever it's called. So this is a spacecraft. It's in orbit around the moon, taking detailed images of the lunar surface. And this one in particular is of the crater of a very famous person in astronomy. Do you want to maybe tell the backstory a little bit, Robert, on this?
Giordano Bruno was perhaps the first. He was a priest, I think 1500s?
Yeah, his endpoint was 1600, I think.
Yeah.
Yeah, so he lived in the 1500s.
He was the first one we have a record of looking up at the stars and saying, there's an infinite number of worlds around those stars, each one like our sun, and there's life on them. And for that, he was tied up to a pole and lit on fire.
Yeah, so that happened in the year 1600. Right. In fact, there is a memorial to him in Italy where this occurred, if you go to the exact site where he was burned to death. And so for his views.
Yep. And his was, well, we won't get into that. I would just say there were some aspects of his that they made it as horrific as they could. Too.
Yeah, so he was burned for heresy.
He was burned for heresy. And, okay, I will get into it. Usually they still left you only semi-conscious. He was fully awake. They didn't do that for him.
He did a lot more, supposedly, than just utter the statements that there's probably life elsewhere. I mean, he did a lot more than that.
And failed to recant and
all kinds of things, stuff. You could argue that never happens today, but really depends where you live.
Right.
If you say the wrong words today, your life could be in jeopardy. I mean, you just have to be aware of the environment that you're in.
Yep. Now, I am going to say something about this LRO picture because it looks so detailed and everything. Everything on there is still on the order of several meters in size. As this frame shows, the diameter of that crater is roughly 22 kilometers or 14 miles. So it's fine detailed and how are we getting that detailed an image? Everything in there is still on the order of tens of meters in size. So, it's not as fine detailed as you think it is.
Well, that's the thing with scale, right? That's why when people take pictures of, let's say, of rocks, for example, they put something beside it like a ruler.
Or a bottle cap.
So you get the sense of scale. Because you can't tell, is this a pit that was created by throwing a small little pebble in a thing of sand or something? Right. Or is this something huge? Right? That's miles across, which in this case it is about 14 miles in diameter.
Right.
So it's that sense of scale that kind of...
And we even make some joke memes about it. I wanted to show how big the Earth is Earth is, so I put a banana for scale in the picture.
Right.
There's even a joke about using the banana for
Right.
scale
Yeah.
out there.
So this particular image from the Lunar Reconnaissance Orbiter, I mean, I like this image. Why? Because number one, you can see the uplifting in the center of the crater where the impact occurred, and material was thrown upwards. And some of that, you can see the upswelling of that material in the floor of the crater. It's not nice and flat. And by the way, this crater is on the far side of the moon.
Right.
Not the dark side.
The far
side. There is no dark side to the moon. It's a misnomer. People think the other side of the moon that we can't see from the Earth is somehow in perpetual darkness, and that is not the case. The only time it's in darkness is it happens to be nighttime at that point in time. And nighttime on the moon lasts about 2 Earth weeks, but the daytime lasts also 2 Earth weeks. So anyways, this crater, then you can see that beautiful, in fact, you can almost envision landing somewhere in the center and studying that material, because that material, notice, has a darker color than the surrounding walls of the crater itself. So chances are that material was brought up from deep underground, under the moon's surface, and brought up to the top. So it's fresher looking than the material, that was near the top of the moon itself, the crustal area. So it would be interesting to study that different material. But why we have this, or why we're mentioning it today, is that an asteroid that's actually in orbit around the sun, this asteroid has an orbit of about 366 days, and it's at a distance of, it varies from about 1.1 times the distance of the average distance from the Earth to the sun, what we call 1 astronomical unit, and about 0.9 astronomical units. In other words, the asteroid in its orbit goes a little bit further than the Earth from the sun and a little bit closer as it goes around the sun. It is so close to the Earth's orbit, it's not exact, but it's close, that people get suspicious of those type of objects. Is there any type of relationship of this particular asteroid with the Earth-Moon system? In fact, detailed analysis of this asteroid is pointing to the fact that its composition is lunar-like in nature. It's like the moon. Now, how do we know the composition of the moon? Well, we brought material from the moon back to the Earth and study in detail during the Apollo project. Plus, we can analyze things on the moon. We've had robots on the moon and analyze the materials.
Not to mention, we can polarize the light and determine what minerals are there and all sorts of things. So we don't have to go there. We can do things here on Earth and determine the composition.
Now, the asteroid itself, which I cannot pronounce, it is a Hawaiian name. Robert, do you want to take a shot at that?
I am not going to. Kama'o'aloa.
Okay, close enough. That asteroid has a composition that's nearly identical to the moon. So what we think has happened, this is the cool part, if you like, is that a giant object hit the moon, created this crater that you see here, and some of the material was ejected into space, and out of that material is what you see the asteroid formed from.
Yep.
So the only way to be able to show that for sure is then to get to the asteroid, land on it, right, analyze the material, or scoop it up like we've done in the past, and bring it back to the Earth.
One of the best ways is to do mass spectroscopy and on the oxygen mass ratios, find out what ratio the various isotopes are. So, for those that don't know isotopes, what isotopes are, oxygen has, I'm saying this and I don't remember how many protons it has now. It's 8?
Yeah, well, there's for oxygen, right?
Yeah, okay. And there's one isotope that's oxygen-16, which means it has 8 protons and 8 neutrons in its nucleus. There are other isotopes that have the same number of protons, but they have different number of neutrons. And that's what makes it an isotope. So Earth in particular has a certain ratio of, say, oxygen-16 to oxygen-14. And the moon is slightly different on that ratio, which is one of the ways we can identify lunar meteorites here on Earth, is they don't have the proper isotope ratios. And so one of the best ways would be to go sample this asteroid and see if its isotope ratios for oxygen or carbon or something like that are similar to the moon or Earth, or are they completely different?
You know, number one, it's not out of the question to go and land on this asteroid or somehow get near it and scoop up some of the material and bring it back. We just did that with the asteroid Bennu.
Bennu, yeah.
And scientists right now are studying that material in detail. So we're going to have a lot of cool information that'll come from that.
Some cool papers
Some
coming
neat
out
things,
soon.
yeah.
Absolutely.
So we can do the same here. In fact, it's probably easier to get to this asteroid because it's in orbit like the Earth.
Mm-hmm.
So it's not going to cost a huge amounts of energy, which means a powerful rocket to get to this asteroid should be relatively easy to get
Should
to
be.
it. And here's where your solar cell comes in handy, and maybe an
Yeah.
ion propulsion
And
to
it could
rendezvous with this.
help you equalize speed so you can sit there and grab off more.
Yeah, so you actually physically land on it, not just get
Right.
down close and then grab some pieces, but to actually physically land on it for a while and
Yep.
then come back.
And then come back.
Anyway, so that can happen in the near future. That'd be kind of a wonderful thing.
I think so. I mean, there's just so many cool missions that are on the drawing board, folks. Stay tuned, you know.
Now, the other interesting science news that's come out lately is this paper regarding peptides. So peptides, if you don't know what they are, so they are a collection of amino acids, and amino acids are really important for life.
For life, yeah. Bottom line, your proteins that make and enzymes that make up your body, because enzymes are just very long chain proteins, are broken down into base units of amino acids. So finding amino acids, you found the building blocks of life. Bottom line.
And so what this paper then is suggesting that it's actually a little bit easier to form these collection of amino acids, these peptides in space than otherwise we thought initially.
Right.
And that really is supporting the idea that life, it may not be that unique.
It may be everywhere.
Yeah, it may be more out there, if you like, than what we initially thought. So this is a good, if you're a supporter of hoping that life is abundant in the universe, this is a good thing for you.
And keep in mind, this is not saying life is out there. This is not proof of life. But it is one of the foundations of life. You've got to have, at least as far as we know, you've got to have amino acids to get things going.
And of course, as Robert mentioned, that's life as we know it.
As we know it.
That's the only, and people will say, well, what about life that you don't, yeah, okay, and all bets are off.
Right.
But we only have one example of life as we know it.
Right.
So based on that, this study is showing us that the conditions are more conducive for the formation of life than otherwise we had thought prior to when this research was released.
Absolutely. I mean, yeah. I don't know what to say there. I mean, they're kind of showing that you can get some of these amino acids by simply combining carbon monoxide, and ammonia. All three are things that are found in interstellar space.
Yeah, and so just to give you an idea of how these peptides and where they fit in, you can see an example on this graph. They are a collection of amino acids, and you build them up, and then you're in the proteins.
You're in the proteins. You build them up enough, you're into enzymes and RNA and DNA.
And then you're into life as we know it.
Then you're into life as we know it.
So this is wonderful news then for those of you who like to think that life is abundant, or at least somewhere else, not just the Earth. You know, it'd be kind of disappointing if we end up saying that, you know, Robert, all signs are up to this point in time with all the technology that we have. Life only exists on Earth, period.
I would think that's a mighty big waste of space out there.
Well, that gets the movie Contact by Carl Sagan. That was that line used there. But I'm just thinking, boy, if we're it, should we be better stewards to the Earth? That's the thing I'm thinking of.
Or I would sit there and go, do we need to be when we can just pick up and go to another?
Well, that's my second thought would be we better start populating other places, not to put all our eggs in one basket. Right. And don't even think about humans and how they affect the Earth. But imagine 10 years from now, we discovered an inbound comet.
Right.
Large enough that it can if it hits the Earth, it would destroy all life as we know it. And unfortunately, it's going to hit. And we have no technology that's strong enough to destroy that comet. It's going to hit. It's just a massive object. What would we do?
Yeah. And the answer is there's nothing we can do. I've been in this discussion before. You know, people are all worried about asteroids, but we can spot asteroids. Whereas a comet coming in from interstellar space, or even from the Oort cloud, we won't know it's even there because these objects are dark. So we won't even know it's there till it starts to form a tail, till it starts outgassing. And that's about the orbit of Jupiter. And as fast as these things would be going then, we got 3 months.
Well, imagine if it's a real massive object.
Right.
Because we always think about, oh, we'll set up nuclear weapons and detonate them and blow it up, or we'll drill holes down and light them off like the movie Armageddon and all this other stuff, right? Or Deep Impact, the movie, right?
Right.
But what happens if it's really massive? I mean, really massive. Let's say half the mass of the moon.
What are you going to do? Sneeze at it? Achoo.
There is absolutely nothing you can do.
Mm.
So all our eggs are in one basket. We are the cradle of civilization on the earth, and we don't have
the cradle
anything.
of life. And the thing is we keep speaking in terms of getting humans off. But, there's more life here than just us.
This would make a good case for maybe we should be sending up repositories and different planets around the solar system, which contains like information, different seeds, for example, of different plants, records of the Earth's culture, all of these things, just in case.
Just to set them up there. Yeah.
Just to at least acknowledge the fact that we were here.
Right.
In case there was that off chance that somebody else, some other life form.
It seems far-fetched and, again, like science fiction, but it's something that should be being considered, I mean, we're building places, several countries have built places in the Arctic to storehouse seeds and animal embryos. Why aren't we thinking further than that even?
Yeah, because if the Earth gets destroyed by a giant comet, it doesn't matter where you put stuff on the Earth is destroyed.
Right. So, yeah.
So, but, thinking about life elsewhere, so one of the things we look for, of course, is whether or not we have the different molecules that exist out in interstellar space that would represent the foundational aspect of how life arises. And by the way, we had this discussion before, but it's important to bring this up again. How do you go from something that's not living to something that is alive? What are all the steps from one to the other?
Well, one, you've got to get these molecules.
Now, these molecules, as you see here, this is just a very small subset, right? We know over 200 molecules in interstellar space.
Yeah, I've pulled up a 2005 paper, and it says 129 molecules have been detected in interstellar space.
And now it's over 200.
Now it's over 200. So, first off, you've got to demonstrate that these molecules can be put together.
And it includes amino acids.
It includes amino acids, which we found them in the cometary material we've brought back.
Now, carbon, we're made of carbon.
Yeah.
And carbon wasn't there at the beginning of the universe. We can conclusively show that to be the case. Carbon is forged inside of stars. Mm-hmm. And stars eject that material later on in their lives to populate the space around it with carbon as well as other things. So carbon-based life is not unusual, and in fact, there's lots of carbon everywhere.
Right.
Even out in outer space.
And there's lots of water.
There's lots of water. There's lots of hydrogen.
There's lots of ammonia and methane.
Oxygen is also produced, right? Mm-hmm. Carbon, nitrogen, oxygen, the CNO. It's the basic, things that can be produced in stars.
You've got pretty much everything you need.
So all these different combination of things are out there, these molecules and stuff, that life as we know it arrives from it. But the detailed instructions that go from something that's not alive to alive, we don't have that solved yet. It doesn't mean that some supernatural force, took a wand and then said, will make life out of this rock or something. We're saying from the point of view of science, how do you go from something that's not alive to something that's alive?
And the next step after you get these molecules is you've got to put them all in the same place. So the next step would probably be a cell.
Well, you're building up then complex systems, complexity.
Right. And that's the bottom line is you've got to go from simple molecules to more complicated chains. And to do that, you've got to get all the components in the same place.
When you think of physics, Robert, like you and I delve into physics, what we like to do in physics, it's like the old joke that assuming a cow is a sphere. Remember that?
Assuming spherical cows. Yep.
Right? So what we do is try to make things extremely simple.
Right.
Boil it down to very, very, very fundamental things. And it's much easier to take the laws of physics, the principles of physics, how physics seems to work, and apply to these simple things. The problem you run into, of course, is that things are not simple.
The real world is not simple. I like to tell my students in the lab, I was like, what you study in class is physics land. Physics land is right next door to Never Never Land. Peter Pan stops by for tea. What we study in the lab is closer to real world. This is what really happens.
Yeah, and so you go from that very simple type of situation or artificial environment and to build up our ideas so that they can explain, at least in some way, more complex systems.
Right.
And that's the problem. That's why we can't, a biologist who works in trying to uncover the mysteries of how life arose on this planet can't go from one to the other.
Right.
Right? It's near impossible.
It's near impossible. You've got to start simple and build up the complexity. I was chided by that by my advisor in grad school, as a matter of fact, because I kept going, well, what about this? And what about this? And what about this? And he was finally like, you've got to start somewhere.
Yeah.
Start with this.
Yes. Start simple, and then you can add in different things
Right.
to build up the complexity and see if you can understand those more complex systems from the point of view of fundamental physics.
Right. It's like studying, I'll put another example, studying a stellar atmosphere. You start out with what we call local hydrostatic equilibrium. Hydrostatic equilibrium says everything is in balance. Well, on the global case of a full star, the whole star, this is not the case. You can't even begin to make that as the case. But on a small enough chunk of it, you can. And so you start with that small chunk of the photosphere, of the atmosphere of the sun, and slowly work out and bring in that complexity and start bringing in things like the magnetic field and then the breathing, the pulsation of the sun and things like that. And in the end, you're able to add on as you build up this more and more complicated model.
Well, if you don't follow that practice and you just dive into complex systems immediately, you'll never get anywhere.
You'll never get anywhere. It's too big. It's too big.
Yeah.
It's too big a problem.
It's like trying to build a house and do it all at once.
Right.
Rather than start at the foundation and continue on,
Yeah.
right?
And to a degree, you've also the house is a good analogy too. To a degree, you've got to get the foundation. You can't just put up the framework for the wall and, oh, wait, we need a foundation.
Yeah.
You've got to build up from the bottom.
But, that's one of these sort of things, hopefully, that'll be settled in years to come, and hopefully not too distant, is to actually be able to go from something that's not alive in a laboratory, let's say.
Mm-hmm.
And there'll be a lot of controversy, I'm sure, on this.
Oh, I'm sure.
We can take collection of things, whether they're molecules and all of these things, and actually assemble those things the right way so that we form life.
Yep.
And that'll be done eventually by somebody.
By somebody.
I'm not saying it'll be done legally. I'm not saying it'll be done in the United States. Could be done in some other country.
Yeah.
But eventually that's kind of where we're going, right, at some point.
And I will sit here and say, yeah, there's a whole ethical can of worms that'll be opened up when we even start getting close.
Well, think of manipulation of viruses.
Right.
And there's always this argument, is a virus alive or not?
Right.
Right? And so we can manipulate those viruses. You can think of, biological warfare type of things, right? The military in different places around the world would love to do that.
Where we go in and use a virus to edit
Well,
faulty
that's
DNA.
it. I mean, that technology has really advanced in the last even 20 years. So 200 years from now, where will we be in all of this? Maybe at that point, we'll be able to describe fully, at least theoretically, how you go from something that's not alive to alive. And the reason why I keep emphasizing that is that's where the situation we are now, is we find these building blocks for life. It's not life, it's building blocks for life.
Right.
Just like a cinder block laying in a pile somewhere is not a house, a full done house, right? But how do you go from that to life itself? And if you can understand that, if we can understand those mechanisms that's responsible, then we can be more positive in trying to state this sort of thing is so natural, right? It's just complex and was hard for us to understand, but now we get it, that this must have taken place somewhere else, not just here on the earth.
Right. I agree, and yeah, it's just building on itself. And wow, wait a minute, that sounds like science in general. You keep building and building and building, trying to understand more and more and more.
Well, maybe when we do understand that, we'll be able to know what to look for. One of the things in science, and this happens all in all, and a classic example of this is brown dwarfs. Now, brown dwarfs are these objects that don't have enough mass to allow sustained fusion of hydrogen to helium in their core, so they can't become what we call real stars.
They can't become real stars.
They're failed stars in that sense. They just don't quite have enough mass. So they have a mass less than 8% of the sun's mass.
Right.
That's sort of that cutoff limit. Now, they should form, just like we have planets, just like we have other objects that are not mass enough to be stars. These brown dwarfs should form.
Mm-hmm.
And we could never find them prior to the mid-1990s.
Right.
So if you're looking for something like a failed star, one of the primary places, you just don't look in a random spot in the galaxy. You look for where stars are formed. You look in stellar nurseries.
Right.
So we look in these giant molecular clouds looking for objects that don't have enough mass to become real stars, these brown dwarfs. And we could never find them initially. And throughout the 1980s, people were starting to think, especially in the late 1980s, maybe there's something we're missing. Maybe there's some physics that somehow those objects don't form.
Mm-hmm.
Right? Or the conditions are such that to form them is fairly rare. So it makes them very difficult to find. People were envisioning that. And what do I need to change in physics then that will allow that to be the case, that would not allow these type of objects to form, or at least they'd be very rare. And they could never find anything. And then finally, in the mid-1990s, we discovered the first brown dwarf.
Right.
And since that time, we've literally found, I think the number's up to like a couple thousand now or whatever it is, right?
Right.
So it's like, if you don't quite know how to find something, right, it's hard to find. But once you find the first one,
now you know how.
Now you know what to do to find it. So let's use that analogy for life. Mm-hmm. If we're looking for life elsewhere, what do we really need? How would we recognize the fact that we found something that was alive, quote unquote?
Right.
And I don't mean like a dinosaur walking on the surface of Titan or anything like that. I'm talking about, very small type of systems, right? Complex systems that might be microscopic in size, or even nanoscale in size.
I like that point, because I think that's the life we'll find ubiquitous.
Yeah. So imagine you take your pet dog to Mars, and of course he has his special spacesuit, a canine spacesuit, and he goes and he digs a nice hole on the surface of Mars, and we quickly sample out the bottom of that pit that he made. Is there life in that sample of soil, in that material? It was hiding from the strong ultraviolet light that impacts the surface due to the sun. The fact that Mars has very little amount of an atmosphere, has an atmosphere, but is very, very thin, right? Yes. So most of the ultraviolet light would just impact the soil directly. So life went underground in order to survive.
Right.
Is that the case? And if it is, how do you recognize that there's life like that?
Mm-hmm.
When we're missing, we have a big question mark, and how do you go from non-living things to living things? That might hinder our progress in recognizing life. Now, this reminds me of back in the mid-1990s when, remember, supposed nanofossils were found in an asteroid, not an asteroid, sorry, a meteorite that was found on the surface of Antarctica.
Right.
And so that's still a little controversial. I think most scientists think, no, it wasn't the sign of life itself. But the problem is we don't know really what to look for that you could say, hey, that's what you need to know that there's life. Therefore, there is life. Everybody will agree on this.
Right.
And that's not the case. I think even to today, we're not quite sure.
I think we had a discussion that, even the techno-signature molecules, we have nothing here on this planet that produces them in nature. But does that mean they're not produced by some process in nature? And the answer is no, it doesn't preclude that. Just because we don't know of a way doesn't mean there's not.
Yeah.
So it's going to take a combination of all these things, and knowing the conditions at which this happens would be a big jump. There's all the conditions, and here's this signature.
We have a field or a branch of astronomy called astrobiology.
Mm-hmm.
So it's cross-related, of course, with biology. And some people laugh and say, well, we only know of life on the Earth. How can we have astrobiology? Well, it's not just to study other life forms, because there's only life forms here on the Earth that we know of right today.
Right.
It's to study the conditions that allow life to arise. If you're interested as a young person into trying to explore how you go from non-living to living, astrobiology is one of the routes to get there.
Yep.
To go from these simple molecule things that we discover out in the universe, and how do you combine those collection of things under the right conditions to form life itself. It had to have happened. Why? Because there's life here on Earth.
We're here. Yeah.
But is it very rare? That's the thing.
That's what we want to find out.
Now, I know, Robert, you always make this distinction between thinking that life is plentiful. It's just not intelligent life that's plentiful.
I will die on that hill.
Right. So maybe you should explain a little bit in case nobody knows what we're really talking about at this point.
I think that life is ubiquitous. It's everywhere in the universe. Okay. I think it's going to be microscopic because there's a few, as the Fermi paradox says, there's a few great filters. You got to go from that simple cells to complex critters. So you've got to get cells cooperating with each other to form a larger organism. I don't think that's an easy jump to make. I really don't. I have nothing to base that on, mind you, but I don't think that's going to prove to be an easy jump. I don't think that going from there to intelligent critters is going to be that easy a jump.
Now, maybe you should define what intelligent means.
I'm thinking tool using, art forming.
Could you use a definition, or would you be happy with this definition? A civilization that has a space program.
That would definitely be a hallmark of intelligence. You can't get to that without intelligence. Absolutely.
Okay.
So the reason I say intelligence is a halt. Something that stands in the way is people don't realize it, but the power of this 3-pound lump on top of your neck takes 1/3 of your caloric intake. If that lump, our brain, doesn't provide you with a strong survival advantage, it isn't going to develop. Okay? It's just not going to happen. So forming a big brain, which I think is kind of a hallmark also of intelligence, requires a lot of energy input. It's not going to happen unless there's some survival advantage. Lions don't need it, for instance. They have to be smarter than their prey, but they don't have to build rockets. And so that's why I'm of the opinion that life will be ubiquitous. Complex life will be a little less so, and intelligent life will be a rare thing.
Yeah, because you could think of some water planet.
Mm-hmm.
Wasn't Mel Gibson in a movie, Waterworld, or something?
That was Mel Gibson. That was, what's his name?
Kevin Costner?
That was him, Kevin Costner.
So in Waterworld, so it's a planet made totally of water, right? So imagine that you have a water world where there's dolphins everywhere. Dolphins are highly intelligent, but they have no need to build
a rocket.
Yeah. So our definition of intelligence, of course, is very coarse-grained, right?
Right.
We got to use something, so let's just use the fact that if you are creatures like us in the way that you had both land mass and water, that you want to explore the rest of the universe. You had intelligence to realize there was something beyond your planet.
Right.
And then eventually you would reach that point where you could develop that. That type of life is, from your point of view then, and correct me if I'm wrong, is extremely rare.
I think that's extremely rare.
And that solves the reason why there hasn't been any visitors.
Right. Because
the space between us and the nearest intelligent life could be another galaxy away.
Could be, yep. We could be it for this galaxy.
Yeah.
Is it out there? I believe that's a non-zero chance as well. But we may be it for this galaxy. I hope not. I would like to meet our counterparts. But, yeah, I don't think there's going to be a interstellar federation of intelligent species.
So we don't have to worry about getting assimilated by the Borg anytime soon?
Right. Or maybe we do, because there's an off chance that type of life is what intelligence is what developed. Look at ants. So intelligence that developed from a communal consciousness may not be an odd thing.
Yeah. Or maybe the most efficient way
It might be the most efficient
way of developing. You never know, right? Yeah.
So,
Anyways, but these are all very interesting questions, of course. And if you like to explore those sort of things, I mean, come to the University of North Dakota. We have courses both online and on campus. And if you come here, stop by Robert and I's office and say hi.
Say hi.
So hopefully get a huge influx of students coming this fall who are interested in higher education and exploring, the world, essentially.
Exploring the world, the universe,
It's nice to, if you didn't finish high school, you can, of course, come as a more mature student, right?
Mm-hmm.
But the other thing is, never stop learning. That's the most important. Whatever your goals are in life, and it doesn't have to be to go to university, of course. It could be do anything at all. But, it shouldn't stop you from reading about things beyond what you do for your work.
Right. I mean, I work here, but I'm also taking a class or two myself. So it happens.
Yeah.
You should do it.
I mean, that's one of the things I think that's worth living is to explore what's out there and keep learning about new and interesting things.
Absolutely.
Now, Robert, our next podcast will be next Tuesday at 3 p.m. Central Daylight Time. So that'll be on April the 30th, the last day of April.
April 30th. Yeah, it will be the 30th.
Yes, because May 1st will be the following day on Wednesday.
Payday.
Yeah, so we're getting there. This month is almost done.
Yep.
Now, we always leave you with a quote or some kind of an excerpt from a book or something at the end of the podcast. Today is a quote by Gentry Lee. I don't know if you recognize that name.
I don't recognize that name.
If you watched a lot of things about the solar system, like on TV channels, Gentry Lee usually appears there and gives a little, interview type of thing when you talk about like exploration of different things like Mars or Jupiter, Saturn, and so on. So he's actually the chief engineer for Solar System Exploration Directed at NASA's JPL.
Okay.
And he's been on many of these missions, and he's had a knack for giving quotes. And they're beautiful, right? A lot of energy, a lot of passion.
Kind of like Yogi Berra and Bob Uecker.
Right. And so if you're interested and listening to somebody who's really into this, you can really get behind it, really get caught up in the moment, he's the perfect person to listen to. And so here's a quote from Gentry Lee. Once you set your eyes on a planet out there, Earth-like, in the Goldilocks zone, once we think we have a chance, we will develop the techniques for interstellar exploration. And the payoff, once we get there, is beyond belief.
Absolutely.
Thank you very much for listening, and
Thanks,
we'll see you
folks.
next time.